Okay, so yesterday we talked about all different types of definitions. We defined what a line was, a line segment, planes, points, and things about those things as well, like things being coplanar, things being collinear, bunch of different terms. We also looked at pictures of what these things looked like. So today we're going to focus on line segments in particular. Um, so we're going to really focus on the distance between line segments and how we can find those distances. So if we have like a normal line, those lines go on forever and ever. So we never really can know the distance of a line. But when we're talking about a line segment, there is a start and there is a finish. So we are able to find the distance between the 2 points. Okay. So by definition, the distance between points A and B is the absolute value of the difference of the coordinates A and B. Okay, so basically we're going to be taking the difference between the two endpoints. We're not going to see it always like that. Some of the examples that we see are going to be a little bit different than just doing that, but it's the difference between the two endpoints. And it's always going to be positive. If I ask you, like, what's the distance from your house to your friend's house, you're always going to give me a positive answer. You're going to say something like 3 miles. I guess if you're talking about distance in terms of time, you might say like, oh, we're only 5 minutes apart, or something like that. You're not going to ever give a negative value for the distance of something. So that's why we put the phrase here, absolute value. Absolute value makes everything positive. So when we talk about the absolute value of the difference, that just means the difference has to be positive. Okay. And then notation that we see for that. So when we talk about the distance between 2 points, we write that as the 2 letters side by side. I won't put any bars over the top, no lines. It's literally just going to be the 2 letters side by side, and that stands for the distance between A and B. All right. So this talks about it a little bit more in depth. This is a kind of like an extension off of distance. It's a little bit more particular. So this is something called the segment addition postulate. And you actually probably do this all the time. You just don't say, oh, hey, I just did the segment addition postulate. So it's a little bit, I feel like something that you guys would probably have seen before, but not something that you call the segment addition postulate. So before we get started, this should be a 64. For whatever reason, it always gets cut off every year, and I try to fix it and never fixes. So that should be a 64, okay? All right, so in example 1, and I'm going to kind of talk through the postulate as I talk through this example. I think sometimes with numbers, it's a little bit easier to talk about, okay? So this forms a straight line. Okay, this is a line segment. And it says find the distance from the starting point to the destination. So we want to find the distance from S to the destination, which is letter D. Okay. Now, what the segment addition postulate says is if we have a big segment, so this entire segment here, okay, and I have segments that kind of like make up that segment. So for example, I have a segment SR and a segment RD, which creates this entire line, okay? I can take these 2 little pieces, add them together, and that will give me the entire distance, okay? It's like if you go to one of your friend's house and you guys stop to get some water. Then you travel to another friend's house and that's where you end up staying. Your total distance is your distance from your house to one friend's house and then that friend's house to your final friend's house. Okay, you're just adding the 2 distances together. So that's what we're going to go ahead and do here. So from the starting point to the rest area, so I'm going to call that SR, that stands for the distance from S to R. That equals 64. And then I also have the distance from R to D, which is the rest area to the destination, and that's 87. I can say, okay, well, from my starting point to the rest area is 64, and then from the rest area where I ended here to my destination is 87. I can just add those two together, and that's going to give me the entire distance from the starting point to the destination. So let's see, 64 plus 87, that would give me 151. Okay, so 151. And it does have units here. One really important part of geometry is that you should always have units with your stuff. So just make sure that you're writing that as you go. Okay. All right. Example 2, we're going to still think about segment addition postulate, but kind of going in the opposite direction. So in this picture, we knew both little pieces, and you could just add them together to find the whole thing. This picture is slightly different because now we know one little piece, j to k, is 15, but we also know the entire length. What we're trying to find here is this little piece from k to l. So we can think of it the same way that we thought here. This was one little piece plus one little piece equals the entire distance. I'm going to write that here the same way that I have here, but it obviously is going to have different numbers, okay? So I can say this little piece here, which is 15, plus this little piece here. I don't know what that little piece is. That's what we're trying to find. So I'm going to go ahead and just call that x. So little piece plus little piece should equal the big piece, which here is 38. Okay. And then from here, you guys did lots of solving equations last year in Algebra 1. So from here to solve for x, I would just do minus 15. Now, keep in mind, there are some of you that probably could do this without setting up an equation like this, and that's completely fine. I'm just showing, if you're not someone that can see pictures well or comprehend what they're showing well, this might be a nice way for you to think about it, okay? So let's see, 38 minus 15 would be 23. Here I don't have units, so I'm just gonna go ahead and call it 23. Okay? And then the last example like this, it's gonna be kind of the same approach. We're gonna be looking for missing pieces here. And we'll either be adding things together or subtracting things like we did in example 2. Okay? So here we want to find two things. We want to find both QS and we want to find both and also PQ. Okay, so P to Q is this little chunk here, and Q to S is the remaining part here. I'm going to do Q to S first. I think it's a little bit easier. So if I'm looking at Q to S, let's look at this little chunk here. Okay. I'm going to ignore the 55 on top. I'm going to look here at the numbers on the bottom. Q to R is 31. R to S is 30. So Q to R to S, that entire length of QS would be 31 plus 30, which is 61. Now P to Q is not a ton harder, but you have to do some subtraction, so maybe a little bit. But P to Q, I'm finding this little chunk here. Okay, if I know P to Q, I'm gonna look at this half now. Okay, I know P to R is 55, and I know this little piece from Q to R is 31. So I can do what I did in example 2 and say, okay, well, that missing little chunk should be X or whatever you want to call it. And I can say little piece plus little piece equals big piece. And when I do 55 minus 31 to solve for X, write this off to the side here, PQ would give me a total value of 24. So you're either going to be adding segments together to get a total, or you're going to be subtracting from a total to get a little piece. You're going to go either one way or the other. Okay. And the last thing we're going to talk about in today's notes is what it means for things to be congruent to each other. So in order for two things to be congruent to each other, it means they have to be equal to each other. Okay. And the symbol that we use for congruence is, it looks like an equal sign, and then it has a little like squiggly over the top. I'm going to put a little box around this so we remember what that looks like. Okay. So if you see the symbol, that just means like this is congruent to this. That's what it'll stand for. Okay. Kind of a rule of thumb too, when we're talking about things being congruent, it usually means we're talking about like this segment is congruent to this segment. Notice I use equal signs when I'm referencing like numbers, okay, like this. When we're talking about things being congruent, it's usually like a segment is congruent to a segment, not 3 is equal to 3, okay? So I'm going to put in quotes here. You'll see letters when we talk about congruence. So again, it'll say like FG is congruent to HJ, okay, something like that. And I'll maybe put that here. AB is congruent to, like, let's say CD. Okay, so you'll see it with letters instead of numbers. Okay, so for example 4 and 5, we're definitely going to at least do one of these. I might not do both. We want to know, given these coordinates of these segments, are the two segments congruent to each other? So step number 1, we need to graph it. Okay, so I'm going to graph letter F. 1, 2, 3, 4. 1, 2, 3, 4, 5. I would label as you go. This one's at -1, 5. And then we're at 3, 3 for H. And then 3, -2. And that's for J. And these are segments. I'm going to go ahead and connect them with straight lines. Really no other way that you would connect it. They're two separate segments. It looks like this. And I want to know if they're congruent. So in other words, I want to know if the two lengths are equal to each other. So I'm going to go ahead and just count boxes. Okay, so we have from G to F, 1, 2, 3, 4. This is 5 boxes. So I'm going to say GF equals 5. And then from H to J, it's 1, 2, 3, 4, 5. And keep in mind, yes, I went down on my graph, but I wouldn't say that the distance or the length is -5. That doesn't make any sense. So that's where the whole like absolute value thing comes into play. So this is just a length of 5. Okay. Since they equal the same thing, the two lengths are equal to each other. So when it asks, are they congruent, we would say yes. And more specifically, we can say FG is congruent to HJ. Those two segments are equal to each other. Okay, we would do the same thing for example 5. You would plot the points, count the boxes, see if they're equal to each other or not, and then answer yes or no for that part. Okay. All right. Last example here, we're going to still do things with segments, but we're seeing variables now instead of just numbers. So a little bit trickier, but still the same concepts. So I always recommend drawing a picture when one is not provided for you. So I'm going to go ahead and draw as I read. So in segment RT, I'm drawing segment RT. In that segment, RS equals 2x minus 8, ST equals 3x minus 10, and RT equals 17. So we see some S's in here, and you might say, well, I have no S's drawn. So we need to create an S somewhere between R and T. It does not have to be directly in the middle. In fact, it probably really shouldn't be, but somewhere between the 2 points, okay? And again, RS is 2x minus 8. S to T is 3x minus 10. And R to T is 17. So I am going to think of it the exact same way that we did example 1 on this previous page. We said little piece plus little piece equals big piece. Little piece plus little piece equals the big piece. So I'm going to write that how I see it. This little piece plus this little piece equals the whole thing, okay? From here, we're going to combine like terms, which you guys hopefully should have done a lot of last year also in semester 1. So 2x plus 3x gives me 5x. And then I have a negative 8 and a negative 10. Together, that gives me negative 18. Oops, that should say equals 17. Sorry about that. Okay. And then from here, we're going to solve for x. So first step would be to add 18 to both sides. And then to divide by 5. Ran out of room there a little bit. So x should equal 7. Okay. Make sure that you're always reading the directions. Here it says to solve for x, but then it also says to find the measure of each segment. So what it's asking for is the segments that are not given. We obviously already know r to t, but we don't know the length of r to s and s to t. So what we can do is plug in what we got for x and simplify. So for r to s, that would be 2 times 7 minus 8. 14 minus 8, rs should be 6. Same thing for s to t. We would do 3 times 7 minus 10, and that would give me st equals 11. Right, in geometry, it's really common not just to stop at x. I know in Algebra 1, you guys are always just solve for x, solve for x, solve for the variable, solve for y, solve for z, whatever the variable is. That's usually how it goes. In geometry, we usually go one step further. Okay, and then in letter B, it would be literally the exact same thing. I'm not going to go through it, but you would have the exact same setup, just different numbers and variables that you would have.